Okay, so in this one, we're going to talk about what I would usually do in like 5 days or 5 years in like 30 minutes or 40 minutes or so. The idea is mostly to expose you to all kind of concepts. We plan to have a GPU-oriented day of our talks, not necessarily graphics-oriented, but also like machine learning and like everything around it. And sometimes later this year or the beginning of next year. But this one is actually going to both recap what I told you before, like something that we did in 2020, and get us prepared to like the next topics. So basically, there are two parts. All kind of like very basic stuff without libraries, like the mini PSG mini Linux framework, that everything is linked, compiled linked statically and runs BusyBox. And the other part, the other conceptual part, the logical part, would be one that we use like fully fledged environment, like the one that I'm running right now that shows you this presentation. But I will not necessarily organize the talk in this order, but I'd rather split it to what is using graphic acceleration and what is not using graphic acceleration. And while discussing it, I will lay the foundations of what is graphic acceleration, why do we need them, why do GPUs have the capabilities that they have, and then Vadim from ARM will go and explain us much more about that and with very practical things. So I'm going to give a little taste of everything. And as always, the objective is that if somebody is like really interested in these things, they can go and reproduce the steps at home. And I already put several videos in the YouTube channel, as I showed before. So there is the playlist like somewhere, and yeah, so it's going to be under here. So there are also some Android-related things in very bad quality that I like took with my phone. But I suppose you will live with that if you're interested in that. So that is our scope. So let's start. I'll start with a recap of what we did in 2020. There are some slides here that I will go over like very, very, very quickly. What we achieved is the following things, graphic-wise. After running QEMU with very minimal kernel that is like a couple of megabytes, like almost nothing, we did something very minimal, and then we started adding all kind of capabilities, like VGA con, which means that we can communicate with, like with a VGA screen, okay? VESA frame buffer that enables us to use VESA modes. I'm not going to talk about it too much. Like x86 BIOS knows how to do all kind of things. Older graphic cards knows how to do all kind of things, and VESA is a standardization that allows us to achieve very nice resolutions and what's known as color depth, like how many bytes you have to represent like each color, each pixel, and we get that. So we added to our minimal system both the capability to display graphics, okay, not only via like a UART, but only via like a VGA screen, and also to get input, right? So you don't need any Linux, you don't need anything for these things. If you use like x86 or any other application or any other architecture, then there is earlier code that knows to handle things. It can be a UEFI, it can be a legacy BIOS, and like in legacy BIOS, you don't need an operating system. You have these interrupts, X10, X16, for like graphic services or keyboard services, and you're done with that. But we did show other things, and we did present other things. And some of the things that we presented was actually how Linux displays graphics. So we reasoned that there can be an element that is called frame buffer when we log in and then get like our nice console, enter username, or like see a boot animation, or see the penguin when we boot Linux if a config fb logo is there. Then this is the part, the logical part responsible for that, but it also needs to understand how to communicate with the drivers, whether they are BIOS or some GPU, okay, some video card. And at the end of this process, it comes like to a display. So we reasoned about that. We also reasoned that this frame buffer is not necessarily necessary, and this will come important when we talk about DRI, because it's a concept, okay? And when this concept exists, then there is an intermediate driver in the Linux kernel called frame buffer console that attaches things to it. This is a recap from something we discussed like 4 years ago, okay? So just so you know it, this is like the path. and it will be rediscussed here. So it's not out of nowhere. Another thing that I mentioned is that there is DRM, but we didn't talk about it at all. And now we will talk about it a little bit. So in 1 second, I will say something which is pretty much true. DRM enables deep learning, okay? And DRM enables something that is called the acceleration framework, which is relatively new. And by the way, its maintainer is also Israeli, some guy that used to work at Intel. And if you see, and you will see, all kind of like new devices that do AI, and then they will be using something like this. This is direct derivative of DRM, which I'll explain what later. So this is a recap from the past, and now we can go back to our present day. Okay? So this is also like there are videos for that, and it's in the playlist, and everything is fine. So our agenda is this little recap. I'm not going to repeat the examples. I'm going to add to these examples. We saw, we booted QEMU there, we booted Linux and so kernel, and we had a frame buffer device to which we plotted. So I will just show a little demonstration of what it means to write something to a frame buffer, just to keep us like connected, and then I'll start showing something new. Like the first parts here, we already seen them, and BusyBox fbsplash, we did not see it yet. And there is something very nice in it. It's open source, it's simple, it's tiny, and if you want to go and explore a concept, you can go and do that. There are, the graphics libraries usually divided into two. Whatever is in the kernel, and all kind of system calls, including all kind of like all kind of I/O controls on some device nodes, like dev fb0, and libraries because you're not going to just go and rewrite everything yourself, even if you theoretically could. So this is very dominant, and nobody who is sane enough does anything without libraries. And in the accelerated world, like the minimum things that you need to do is use a library that is actually very tiny called libdrm, and I still have not explained what DRM is, and it does a lot of things for you. So we're going to talk about this and then start shooting demos of all kind of like 2D graphic libraries. Later, we will have a motivation for GPUs and talk about the direct rendering infrastructure or direct rendering module, which is known as DRI. You will almost always hear it as DRM. Anybody want to tell me what is DRM also? Exactly. Are you from Cisco? No. NDS? Cinemedia? Yeah, so there have been like many people and many excellent people actually in Israel working on DRM. Tons of them, yeah, you're smiling because they're from Malchut from Jerusalem, and like this was their thing, like for many years, and I spent there quite some time. So we'll get to it in the second part. I just want to say seriously, like this is the infrastructure of graphics, or of graphic cards and of machine learning. And I was going to start like with a joke before we said, okay, like we need to respect everybody's time and say, okay, what are what are like GPUs used for? And I would expect everybody to say crypto mining or stuff like that. But yeah, they're used for a lot of things that have nothing to do with graphics, but they were first developed for graphics. So we will see like a pretty good evidence when we start seeing some graphics that may not seem so trivial to why and how they exist. Speaking of libraries and framework, there are tons of framework. In this lecture, I'm not going to cover all of them. I'm giving you a second to look like at the flow. My personal strengths are probably Qt and GTK and LVGL and all kind of AOSP things. But yeah, there are tons of libraries. Disclaimer, I don't like bloated root file systems. So I would always say, don't put anything unless you really need to, and this lecture will go like in this concept. I also don't like putting screenshots. I prefer to do demos. Maybe it's a mistake because it made me put like 5 hours of videos in YouTube. I already put them, but some of them will be published after this talk. Like, so this summarizes everything, and there are full steps for everything if you want to be rigorous. Warning, in order to not screw up forgive my words, the lecture, and then I'm going to use QEMU. Something extremely important when you use virtual machines and want to do pass-through of any device, not necessarily graphics, the best thing is to have a dedicated device that never meets your host. Okay, that's the best thing. Now, my particular computer has a feature that is not that is available called like SRIOV. It enables to take like a GPU and expose it to guests, to virtual machine guests, even if it's like a single GPU, and enable some sort of GPU pass-through. But for all these kind of things, when virtualization is concerned and you're not using remote display protocol like SPICE or like VNC, you're not going to be very happy with the results a lot of times for reasons that I will explain. So here I don't know if I will explain like everything. There are some things like in the videos as well. But just so you know that the architecture here is that QEMU is using a host tool to pass GPU calls to the machine itself, like to the GPU itself. And if these modules do not implement all the possible calls that they need, then you may see some graphical artifacts. This is something to note when working with VMs. So the guideline is if you want to work with VM, buy another graphic card and make it something that is well supported, and then install all the drivers you need, all the firmware you need on the guest, and let the host never see it, and this is like the way to go, okay? Now, so this is some of like these disclaimers. Another thing, if you do graphics and you just want to work with like a minimal initramfs, like our first system, like before PSCG Devos, that it was like the PSCG mini Linux one. If you put everything in a graphic and you have all kind of images that you want to put, for example, on a splash screen, then those images would usually be, even if in PNG they are like a couple of hundred kilobytes, they will be like 100 megabytes or 50 megabytes, like easily. So you need to be mindful of the size of your memory, because if you put RAM disk that is like too big, your kernel will panic. You will have no idea why, because who does this kind of thing, and the errors will not make sense. And the reasons is that like the RAM disk will like overlap with the kernel. You don't have enough memory, all kind of thing like that. So this is it. Another thing, for some of the demos, I will be, because of this reason, I will be mounting a file system from the host, but I'll do it like in a simple way. There are several different demos, and some of them I actually prepare like a system image. In some, I just do like some network mounting that is trivial, and I put some explanation of this in some of the videos. Having said that, let's go. Our objective is this. On the left-hand side, we have, it's not Google. There was not enough space to write Google. My sincere or not so sincere apologies. On the left-hand side, we have what we call the frame buffer. We want to be able to have like a matrix of coordinates and say, I want this intensity. It doesn't exactly matter what the model is. If it's RGB, if it's some other model, it doesn't really matter. But we want to put colors, intensity, lighting, pixel, whatever, and that if we are able to put them by like X, Y, for example, and if this is the screen, then we want it to show very nicely up on the screen. So there is a process in between. This is the simplified objective of this entire talk, okay? So I'm not going to talk into too many things, but there is some glossary. Like there is the resolution, there is the timing, there is the color depth that I briefly mentioned. There are the input and signal types. There is how I connect my graphic card into like the outer world. So here I have like a HDMI. I could have like display port. I could have like a LVDS. I could have a VGI connector. I could have a DVI connector, so on and so forth. Why is it important? Because in the last mile, when the kernel wants to actually emit some output somewhere, it needs to know how to do that. But there is a path way before that, because somebody just wants to say, hey, XY, paint green. What does it have to do with the signal type? So the fellow that does almost all of the translation and everything is, in the Linux case, the Linux kernel, okay? So it needs to know of that. And by the way, if I go and plug my device, it also has to do with it, because when I connect something to the computer, for example, this is like my internal laptop. I can go ahead and the kernel exposes some information because it gets from the device that I connect, from the display, all kind of information. This how we can say, oh, this is the kind of device, or in this case, some Dell monitor. Do I have like a drivers for that, or how do I do mode set for that, and so on and so forth. Other thing, mode setting. If I connect a device, any device, I want to make sure that the device knows like its resolution. Okay, I can have like this huge screen over there, and it can be billion by million pixels, but I need to tell you, hey, this is the resolution that you need. Otherwise, if I tell you that it's a 1024 by 768, then you will see probably an image that will destroy your eyes. So the operating system also needs to tell you that. And if you have been here for a long while, maybe you know the VJ equals ask param. I demoed it like in the past. So there are several ways to do that. All of them are derived either by some firmware or some BIOS or some UEFI, or you can do it like via the kernel. Now, the examples here are on x86 because it's like the easiest, but we already seen all kind of architectures. We saw ARM, we saw ARC64, we saw RISC-V. So in each architecture, you just need to see, okay, how the display is connected, and then do similar things, right? So, other thing that has to do with our terminology. This is not exactly accurate, but there are display servers or display protocols like X, Wayland, and there are the lines between everything that makes things desktop, like the desktop environment, and display manager, whatever asks you like for like the password and select one, or so the window managers, whatever enables you to say, hey, this is the concept of window, this is how I manage several things. Compositor that can take several components and like merge them together, and then let like the final graphic destination see what's going on, and so on. So my hope and my objective is that like from this talk and Vadim's talk and the talks like in window and the talks in YouTube, then people will come up like with their own talks, either because they learn it and interested, or because it's their specialty. These topics are huge. I trained courses about like Linux graphics stack millions of times for entire weeks. Like, okay, an entire week. It's huge. It's a huge topic. It's a huge topic. It's a huge topic. Okay, so I already mentioned like some examples of how we get some information like from the sysfs. And if the device supports it, like in this particular laptop, I can go ahead and cut a value into this is device PCI. This is how the display is connected here. This is DRM, the display card. This is DRM card. We'll talk about it later. This is like the connector. Intel backlight. If I put all kind of like values here, I'm not going to do it on terminal out of respect for our time. But you could see that it actually, you cannot see it. I can see that it's actually going to change like my display brightness. So like communication can go both ways. Depends what the device exposes. So this is device. This is like the same size. This is device that exposes less things. This is device that exposes more things, like the other terminal. Okay. Plug and play. How do we live in a world where I connect my HDMI cable or whatever, and it just automatically works? Because there are events in the Linux kernel or in other system, and the kernel can feel it. Like we can feel carrier like in network. Of course, it's other technology, but we can feel it. So I can go ahead, and if things don't work, also check sysfs, see if something is enabled, or if it is disconnected or connected, and so on. So before we started, I did mention that, hey, like this is like a desktop environment, and you see like all kind of things, and I gave some terminologies. Let's see more or less what we see. So if I come, and you know what, I can start like with the end because I have already example for that. I will run it. I had an example for that. I think this should be good enough. It will boot, and then we'll see some things. If I run, by the way, this is like the boot logo. We see several penguins because of, what does it mean? The number of processors. This is like the SMP parameter. Okay? So I stalled time because I wanted you to see what happens when I boot like an environment, okay? So I have here like a user. This is a GNOME environment. And if I click it, this is like the display manager. It greets me. It tells me all kind of things. I can go and select a desktop environment like GNOME or a KDE that is based on Qt and so on, like this, all right? And then I can connect and see like, I don't even know what I selected, but then see like more graphics, okay? So the idea is that like in a desktop environment, I will have like the display manager. I will select which one I want, for example, GNOME. Is it possible that I put the wrong password? It doesn't matter because I don't want to show it anyway. And it will have all kind of components and windows like I showed, or like logos, like little cursors. And then it will do two things. Like it will be able, like a window manager. Sometimes all of the components are the same component, like Matter and GNOME. Will know, hey, this is the position of the window, this is the status, it's maximized, it's minimized, it's above this, it's below this, and so on and so forth. And all of these things, usually they will be called, including panels, okay? Including the cursor, including the windows. They will usually go via some protocol, like from a less privileged process, for example, into a more privileged server. It's like this also like in Android and everywhere actually. They will go to something called compositor that can take them and put them on the screen, blend them, like so if they're transparent, if there are all kinds of effects, if there is this, that, and then they will go like to the relevant kernel drivers that will say, okay, this is what we do, this is how we do. Who does it say to? To the actual hardware, like to the GPU that has like the connectors that tells. So this is how things would usually work there. When I speak about these things, in our systems, they're very, very, very complex. Here there are like three different things. On the right-hand side, you can recognize good old X11. It can get input, it can get, it can communicate, it can via network also with external clients. This is why you can do SSH-X or -Y and do X11 forwarding. And essentially, it can do all kinds of things remotely, often like in your own computer, run a display protocol with a server that knows how to composite it, and then it talks like to the hardware itself. So this is X. On the left-hand side, you have Wayland. So we have here DRM, which is responsible for accelerating, like in the kernel. We have KMS, that is the mode setting, like resolution and stuff like that in the kernel. And all of these things that we have here, like let's say KDE Plasma or GNOME, or like a video player, VLC, I don't know what, all of these fellows, they have a display protocol against something that is called Wayland Compositor, okay? So Weston is like a reference design of that, I'll also show that, but you have like for GNOME Matter and you have all kind of other things like that. In addition to that, both the compositor itself and the libraries, let's say we want to do like an OpenGL game, they can communicate with the graphics subsystem in order to do what is called, for example, one of the things, rendering. Now, rendering as it for itself, it doesn't display, it doesn't do anything with displaying to the hardware. Rendering is calculating, basically. Okay. So in the left-hand side, it's something like this is how modern things work like, and Wayland is now really the de facto standard of display protocols in Linux. But the other thing that we showed also exists, that there is user, it has like a graphical interface. There is kernel and hardware, there's a display server like Wayland or X11, and there is like a window manager, okay? So there is a lot of things here. These systems are very, very, very complex. Now, if you heard about Wayland or X, or are afraid about Wayland, don't worry too much. There is something that is called X Wayland. Wayland Compositor can also work with X clients, but I'll give you a second to look at it, or I'll give you more to pause, like if you see it in YouTube, and we're not going to talk about it now. So, back to our frame buffer discussion. What we have is a user space application could be a terminal, could be console, could be whatever, that wants to write something to the screen. So it can go ahead and write to the frame buffer memory by doing some yoctals to fbn and then mmap. For example, yoctal, hey, what is your resolution? And mmap, give me all the pixels that you have, and then write pixels into this mmapped area, and then say, hey, I'm done, and go ahead and draw. It's called usually page flip, but we'll talk about when you have like multiple buffers. So the idea is that the I'm done, the do this, get me that is being done by drivers, okay? And the drivers can encode things in a way that the display can understand. The kernel can also do it regardless of like the user space interfaces, and the first time you can actually see it for yourself is, for example, in the boot logo. This is like a very good example for that. But we all know, especially those who like hardware here, I had like a little chat before with some of you. We all know that you can even have like a simple device that will, when it powers up, will just show you some graphics and has no Linux and has no nothing, right? It can be like some screen you connect with SPI, it can be all kind of things. So sometimes they're already displayed before you even do anything. Or sometimes you have a bootloader like a Grab or Uboot, or you have some graphics from UEFI that does things before the kernel like starts. So like I said, Uboot, in Uboot you can take a bitmap and do BMP display and then show it. So it's not only that the kernel knows how to do things, like there are several components that know how to do things. But if they can do it, then the Linux kernel can do it. Okay? Speaking of the boot logo, we covered it in the past. What you need is a config called logo, and you need a config frame buffer console. This means frame buffer console in plain Hebrew means when you boot without any graphical display and you have like the user password, okay? This means, or you just get a shell on your device, not on a serial terminal, on your device. This means you have a frame buffer console. And it means you can write, because the kernel implemented a mechanism to draw specific characters, which means that it can render fonts and display fonts. It can say, hey, if the letter is D, then it looks like this, and this is the size, this is the number of pixels it does, okay? And what it also means is that if other can paint to the screen, then so can the Linux kernel. It can blit. Blit means like putting like drawing an image into the graphics. So it can also do that. So we saw it like in the past. I'm just going to show another one of the demos later, but these are like a list of files that are relevant in the Linux kernel, okay? Modern kernels, since version 6.10, which came out last month maybe, can also do like graphic accelerated panics or use a DRM, but that's not for now. We talked about VESA in the past. This is what I meant, like a list of resolutions when we give VGA support. This is called box setting. Because of time, I'm skipping it. But the idea is that if we work with a device, we need to set the resolution. Otherwise, we'll always say, hey, I don't see everything, or I see everything disgusting, and so on. So with frame buffer devices, the way to handle it, the traditional way, would be like a tool called xrender from Xorg, which are a user space library to do the graphics. So I mentioned that we can write all kind of things because there are fonts, and I mentioned that there are all kind of, we can do all kind of blitting of images because other components can. So why can't we? So usually when you have a boot logo or boot animation, which means putting like an image after image after image after image, or doing a progress screen, drawing a rectangle and doing something like that, usually it will be a very simple format that can be parsed, unless you want the parser to be very big. And the format for that, very common format is PPM, and these are like the magic number of it if you're like interested in it. So if you want to replace like the penguin and the boot logo, then this is one of the things that like you can do. Now let's start demoing. So I'm going to go now, and I'm going to get rid of this nice example here in order to show something else. So if I go to one of the demos here. This is a boot animation that I had, and this is like a frame buffer console, okay? I'm not going to talk too much. This is actually also has graphic acceleration enabled. It has both, because I'll talk about it in the second part. I just want to be very quick on that. So essentially, I'm going to just make sure that we see this, okay? And the reason, a proof that we have like a DRM is that the resolution auto adjusts for that. Up. So I put this on top, okay? And what I'm going to do, that's not what I had in mind. What I'm going to do now is copy paste from the slide. Why? Because I can. So look what I'm going to do here. I'm going to write some code to dev fb0. I'm just proving that I can write like from user space. That's what I'm doing like right now. So, you know, like this TV here, and now look, it will paint like, it's supposed to paint like a like the screen. You saw like the TV for a second, so now you will see these black stripes. So what I've been doing here is essentially the following things. I took some random bytes. Thank you, always on top. I took random bytes. I just filled the frame buffer. I don't know the format, I don't know anything, it works. And then I took 0 bytes and I started painting bytes, like 100 Ks, okay? And then I skipped, like, this is like the 6th param. That's what I've done. So I already know that from user space, I can go ahead and affect the graphics. Now, if I knew exactly what is the format of the frame buffer, what do I need to write where? I can do graphics that are more meaningful, okay? So let's go ahead and do one thing like that that is a little bit more meaningful. And this thing will be using, we already saw like a couple of splash screens. When I booted here, you saw like this PSCG logo. You saw this green splash screen, okay? If I modified like the resolution, let me do that. We had like the VGA set, so let's do 344 just for fun. So I'm going to do that. VGA ask, I'll give it. Ask. I need to do, not ask, 344. I will here add like another device. You know what, I'll just do something like this. And I will rerun it, hoping we did not miss anything. So we have the penguin. You see this? Like this gray thing? This was a splash. Did you catch it? This is a splash screen that I've done 4 years ago in the one of the Yocto project things. And this was in YouTube, meetup number 3, somewhere. So this is something that somebody like wrote for me. But it's called fbsplash. fbsplash is a little bit advanced, and I can also, like, the way I progressed here is because it listens on some pipe, and I tell you, hey, draw 10%, 20%, the day it advances it. I can do very similar things with something called fbsplash of BusyBox. So if I came now and I did something like, that's not what I had in mind, like fbdev, and then I'll go fbsplash -s what's e something, e banner compress default. You know what, I'll do something else first. I'll do e banner meetup 16 png. I'll go and cut it. I'll do something naive. I'll cut it into dev fb0. Then I got something but this is still like not the format, so I can probably not like cut those PNGs. So no matter what mechanism I have, I need to understand like the format of translation. So fortunately, fbsplash does it. And if we do fbsplash -s, that's not what I demand. fbsplash -s eBanner compress default. Then look what it gave me, okay? So I bleeded an image and I need to charge, so you need to excuse me.